Greetings everyone, this is non-expert here, back again with another video. Today we are going to be solving problem number 60 and the difficulty it's been rated at is medium. This problem was asked by Facebook and let's just dive right in. So given a multi-set of integers, we need to return whether it can be partitioned into two subsets whose sums are the same. So you've been given an example over here and given the multi-set 15, 5, 20, 10, 35, 15 and 10, it would return true since we can split it up into two sets which are 15, 5, 10, 15, 10 and also 20 and 35. So both of these sets which we have over here are adding up to 55. So that's the reason why the function should return true. So given such a multi-set, we need to return a Boolean value which sort of help us determine whether this particular set which has been passed into a function can be split up or sort of can be divided into two subsets that add up to the same sum. The property over here is that it needs to add up to the same sum, and that's what's the important part over here. And fortunately, we are able to find a similar problem on lead code. So the name of the problem is partition equals subset sum. And if you're really familiar with dynamic programming problems, you've seen this problem. It's a pretty common problem. Um, and as usual, I would sort of urge you to pause this video and check out the link given in the description below and try solving this problem on your own. But as you can see over here, the problem description is ideally the same. You've been given a non-empty array containing only positive integers, and you need to find if the array can be partitioned into two subsets such that the sum of elements in both subsets is equal. So you've been given an example over here as well, which is 1, 5, 11, 5, and you need to return the output as true since the array can be partitioned into 1, 5, 5, which has the sum 11, and also 11 as the second set. And that's basically it. So this is a very common problem, and there are multiple ways of solving this problem. But the most easiest way of solving this problem is the recursive approach. And the way to sort of go about this recursive approach is that you already know what all numbers you have inside your array or your list. So when you have that, you know for a fact that the sum that you're trying to achieve inside one of the sets that you're going to make is going to be the sum of all the numbers which are there divided by 2. That's pretty obvious since if you take this example over here which has 1, 5, 11, 5, what you're going to do is you're going to add all these guys up, divide them by 2, and then make sure that they are divisible by 2, that is that the remainder that you get is 0. That will make sure for a fact that the sum that you have can obviously be divided into two parts, and if it can be divided into two parts, you need to find out whether that target sum that you've sort of calculated, which is sum divided by 2, whether that value can be computed or whether that value can be determined by the sets or the elements in the set. If you don't understand that, that's pretty okay, it's fine. But all in all, what you need to make sure is that the main utility function which you're going to build out is going to recursively call itself and it's going to divide the problem into two subproblems. And the first subproblem is just going to be that you're considering the element which is there and whether you're not considering the element. If you're considering the element, then the target which is there, you need to sort of subtract it with the element which has been considered. And if you're not considering the element, then you just update the index and move on from there. So a bunch of words, but let's just get down to the problem. And before I sort of implement this, I want to tell you that there is one other approach that you could obviously do this recursively, but since you can do this recursively, if you can memorize it, which we can, in our case, we'll be doing that, you can sort of improve the performance as well and work at a better complexity. So the recursive implementation, which I was sort of talking about, sort of works on the premise, which I've sort of coded out right now, will work on the premise of, or rather work on the time complexity of 2 raised to power n. And keeping all that aside, there is one other solution which I'll be talking about in my next video, which is going to be more of a DFS implementation. And in that video, I'll be explaining why the DFS implementation is also pretty popular. But yeah, let's just get on to a solution. So we are going to start with a base condition, which is just going to be, hey, if no numbers have been given to us, then we just return false. And that's just something that we need to start with. Now, one other thing which we sort of need to make sure is, and this is not really a necessity, but I like to do this, is that you make sure that the numbers that you've been given in the array are sorted. So we can do num sort. What this would do for us is, though it would not, theoretically would not the time complexity as such, what it would do in place is that we can add a few checks so that we can stop the iteration or stop the recursion when we have an element which is already greater than the target sum. So in that case, we won't really have to worry about all the other elements. I hope that sort of makes sense, but if it doesn't, don't worry about it. We'll talk about it later. And what I'm going to do is I'm going to use something called as a div mod. I'll explain the div mod in my previous solution as well. It's basically a function in Python which takes in two parameters. And over here, what we're going to do is we're going to take the sum of all the elements inside our num and try dividing it by 2. And then we need the remainder as well, because the remainder will sort of help us understand whether it is divisible by 2 or not. And then the target value, which is the value that we need to check for our subset. So let's just do that. Let's just say sum nums and then divide by 2. Now what we need to do is we need to check whether rem exists. So we just say, hey, if rem is there, then we need to return false. Basically, if you have when summed up together sort of returns an odd value, we need to return false. So that's what's happening over here. If it doesn't, then we sort of move on. And what we're going to do over here is that we're going to make a utility function. Now, this is on you. You can sort of make an inner function. I prefer using an inner function approach. So let's just do that. Let's just say def. I'll just call this dp for now, and we'll just give I index and target value. And what we're going to do is we're just going to return whether this value is returning a true or false. So our main function or can partition function is going to be calling the dp inner function, which is a utility function which is going to take in two parameters, an index and a target. The reason why I'm writing this as an inner function is just because we're going to be referencing this nums and it's sort of accessible over here. So I don't really have to worry about passing it over and over again. So for the index, what we're going to do is, if you've already understood, the approach, you would sort of get a hint that, this is more like a top-down recursive approach, and that is what it exactly is. And the index that you're going to, start traversing from is the last index, and then you're going to, go or sort of decrement from there on forward. And the target is obviously the target that you've calculated, and that's basically it. And then you sort of, move on from there. So let's pass in our index, which is going to be length nums -1, and also the target value, which is this guy over here. Now we can sort of update this target value as such, since we're using it in two places. So let's just call this as total, and it's not the right terminology for it, but for now we just write total, just so that we don't have any misrepresentation of what target is. And now what we have to do is we just have to make sure that we're following all the conditions. So the base conditions for this particular case is just going to be that, hey, if target is already equal to 0, which means that we've achieved for a fact that we've achieved a set which sort of computes to, or when summed up together sort of computes to the target. In that case, we can just say, hey, if target is equal to 0, then we need to return true. I'll just get rid of this pass. And cool. The other thing that we sort of need to make sure of is that, hey, if I've already on an index which is greater than the target, then all the elements before it are also going to be greater than the target. So in that case, I can just return the next values and sort of move on from there. I hope that sort of makes sense. It's pretty simple to understand, but if not, that's also all right. You can just code over here and it'll give you a better understanding of what I'm trying to talk to you about. So you just say, hey, if nums I is sort of already get the target which you have, then in that case you don't really need to consider all the other cases. The other cases, which I mean, is that you don't really need to consider including any of the elements. So all you have to say in that case is just, hey, return dp. Do not consider that case. That is, do not consider the index which is there, do I -1, and do not subtract that value with the target. That's nums I. And the other condition is that, hey, if you've already reached a particular limit, which is if the index is less than 0, then you know for a fact that, hey, I've reached all my limits over there. Then you don't need to move forward from there. So you can sort of return a false at that particular moment of time. So all you have to say is, hey, if I is less than 0, or rather target is also equal to sort of less than 0, then you return a false. Basically, you moved back too much, or you've added too many values, due to which the target value is now negative. And when that happens, you just return a false. And now coming to the main two subproblems which we have, which is very, very simple. You either consider the case of including an element, uh, and when you consider a case, you do the same decrement of I minus 1, which is your index. But when you do that, you also make sure that you're reducing the target, which is summed up value, by the nums value. So you can do that. That is that you're considering the case uh, of the index, and the other case is that you do not consider that particular value at that particular index. And that's basically your two subproblems, and that's the way to go about it. Pretty simple, there's not much here to it. I can try running this code and hopefully this should run fine. Ideally, I do not see any reason why it does not. Okay, cool. So it is running, but there is a little bit of an issue, and the issue is that this solution is sort of working at a complexity of 2 raised power n. So when I try submitting the solution, it's going to most likely throw time limit exceeded, and that's not something that we want. So the way to sort of go about it is, obviously you can use dynamic programming, but you could just update this recursive solution yourself. And the way to do that is by using memoization. Memoization, I've already explained it before in my previous video. And if you did not watch that video, that's fine. I'll try explaining it again. So all you're going to do is you're going to maintain another variable called memo, which is going to be a dictionary, and it's going to take a key and a value. So the key is basically going to be the parameters that you passed inside your function, which is the dp function, and the value is going to be the value which has already been computed before. I hope that makes sense. But the more important thing is that I and target are the two parameters that you're going to be considering inside your memoization or memo rather variable. So let's just do that. So that is actually very, very simple for us to do. To be very honest with you, before I do that, let me just push this guy out. Actually, to be very honest with you, we don't really need that guy right now. Just for the sake of conciseness, I'm just gonna remove that value and just put in the memoized solution. So all I have to do is I just have to check whether I comma target, which is the two parameters which have been passed in, are present inside my memo variable. And if they are, then all I have to do is I just have to return that memo value. So let's say return this particular guy. Simple enough. And I'm just going to cheat a little bit. I'm just going to copy this guy. And instead of return over here, what I'm going to do is I'm just going to, update the memo value with this guy over here, and just say that, hey, instead of returning whatever values was, being called recursively, you sort of store that value inside your memo. And now all you have to do is you just have to return that guy itself. So when you do that, what's happening in place is that whenever you have a particular function which is getting called, which has the same parameters and the same target and the same index, and it's already been computed, you don't have to go through the entire subproblems again. You can just sort of pick it up, fetch it from the memo, and just return that. And that's basically it. This is like the way to sort of do memo here. You don't really have to get into the entire case of building out a 2D array. If you're familiar with that, then awesome, you can sort of do that. It's easier to visualize it. But all in all, I feel like implementation wise, this is this is much better. So oh, and yeah, one thing which I sort of forgot to mention is that sort of work out the complexity of or rather the space complexity of sorry, m into n, and that's the bigger complexity. And for the time complexity, you're working at a complexity of m into n into n. I hope that sort of makes sense. If it does not, that's quite fine. Just try understanding it from perspective of performing memoization, and that's just it. So let's just try running this code. Let's just see that this is working fine or not. It is. Awesome. Let's just try submitting this. Hopefully it should get submitted. And awesome, you can see that's faster than 79% of the Python online submissions. Memory-wise, not doing so well, primarily due to the memoization dictionary, but that's all right. That's like a trade-off over here, and that's not something that we can help for now, at least. And that's basically it. There's not much here to the solution. It's a pretty simple solution. All you've done is you sort of broken down your problem into various subproblems and sort of moved on from there. And this is a very simple problem just because you understand for a fact that you're not even returning the list, you're just returning a true false value. So you know that either the value is going to be true or false based on the fact that you're considering the element to achieve your target sum or not. And that's basically it. There's not much here. If you have any comments, do leave it in the comment section below. I would love to handle any of your queries. And if you did like this video, do give a like and do subscribe to our channel. We are discussion over here and we would love to have you. As mentioned before, this is the recursive implementation and I'll be moving forward with the DFS implementation as well in the next video. So make sure that you check that out as well. And if you've already subscribed, you're awesome. We all know it. And have an awesome day. Thank you.